Mathematics in Modern World Overview. Most of us think of mathematics as patterns, fractals, addition, subtraction, multiplication, division, fractions, or whatsoever. But in reality, math is all about having fun. It allows us to accomplish a great deal. Mathematics aids our comprehension of the world around us. Similarly, we use the world to better understand mathematics. There are two major themes in mathematics philosophy that may be useful in this regard: mathematical realism and anti-realism. Like realism, mathematical realism claims that mathematical entities exist independently of the human mind. It tries to convey that humans discover mathematics rather than inventing it. Mathematical anti-realism, on the other hand, claims that mathematics is a creation of the human mind, carefully crafted to make formal statements about nature in order to aid our understanding of the universe's behavior. Now, there's a fascinating question about which no one can agree. Was math truly discovered or invented? Well, it makes no difference to me whether it is discovered or invented. The main goal in this course is to comprehend the nature of mathematics, appreciate its significance in different endeavors of humans, and relate mathematical concepts and principles to concrete applications in real-life situations.
Now, much more than arithmetic and geometry, mathematics today is a diverse discipline that deals with data, measurements, and observations, from science with inference, deduction, and proof, and with mathematical models of natural phenomena, of human behavior, and of social systems. Mathematics reveals hidden patterns that help us understand the world around us. As a practical matter, mathematics is a science of pattern and order. Its domain is not molecules or cells, but numbers, chance, form, algorithms, and change. As a science of abstract objects, mathematics relies on logic rather than on observation as its standard of truth, yet employs observation, simulation, and even experimentation as means of discovering the truth. In addition to theorems and theories, mathematics offers distinctive modes of thought which are both versatile and powerful, including modeling, abstraction, optimization, logical analysis, inference from data, and use of symbols.
Mathematical reasoning is when a set of statements are provided in support of a claim and the claim derived from these supporting statements. Supporting statements are called premises, and assertions drawn from these premises are called conclusions. So there are two types of mathematical reasoning. First is the deductive reasoning, then second is the inductive reasoning. So for deductive reasoning, it has a structure that is moving from general premises to a specific conclusion. Deductive conclusions are reliable provided that the premises are true. A common form of deductive reasoning is syllogism, in which two statements, a major premise and a minor premise, together reach a logical conclusion. Now, the inductive reasoning has a structure that is making a general conclusion based on specific premises. Inductive reasoning does not guarantee that the conclusion will be true. If the premise is true, however, conclusions are more likely to be true, but it could still be false. One application of using mathematical reasoning in our lives is when, for example, I want to know where my father is when I get home on Wednesdays at 4:30 p.m. I apply deductive reasoning. I know he is either at home or at work on Wednesdays at that time. When I arrive at my house and he is not there, I assume that he is still working. So this is an application of a deductive reasoning. Then another application for inductive reasoning. For example, when I have a headache, I conclude that it is a result of spending too much time studying and reading. However, this does not always imply that this case is true. because I could be suffering from a headache because I am sick. I utilize inductive reasoning in this example, in which one event is claimed to be the result of another.
Whatever forms of shapes, patterns, or designs, they are everywhere around us. Math is everywhere around us, even in health-related areas. One topic under mathematics that piqued my interest is fractals. Fractal is a pattern that the laws of nature repeat at different scales. Fractals are seen everywhere, in the sky, the lightning strikes, the clouds, in river deltas, the plants, your rugs, and us human beings. In the field of our degree course, it is crucial for us to familiarize ourselves with the usual patterns of how our body works and how it should work for us to identify any irregularities in our health. Our bodies are full of fractals. Our lungs, circulatory systems, and our brains, they are full of patterns that are similar to trees. Because the human body is filled with fractals, we can utilize fractal math to measure, characterize, diagnose, and perhaps soon treat illnesses. This is the reason why fractals stood out the most for me in the entire semester of mathematics in the modern world. As a nursing student who aspires to be effective and efficient in her future profession in the medical field, fractals have undoubtedly opened up a new knowledge that will aid me towards becoming my dreams.
A strong impulse for developing mathematical logic came from the attempts during these times to provide solid foundations for mathematics. Mathematical logic has now taken on a life of its own and also thrives on many interactions with other areas of mathematics and computer science. Logic means reasoning. The reasoning may be a legal opinion or mathematical confirmation. We apply certain logic in mathematics. Propositional logic is the fragment of logic where new statements are built from given statements using so-called connectives like not, or, and. The truth value of such a new statement is then completely determined by the truth values of the given statements. Thus, given any statements P and Q, we can form the three statements: the negation of P, pronounced as not P; the disjunction of P and Q, pronounced as P or Q; the conjunction of P and Q, pronounced as P and Q. We start with the five distinct symbols: the T or true, F or false, the not, the or, and the and. These symbols are fixed throughout the course and are called propositional connectives. We also have other connectives such as exclusive or either but not both, implication, which is pronounced as implies, biconditional, which means if and only if. The truth table is used to perform logical operations in math. It is basically used to check whether the propositional expression is true or false, as per the input values. It consists of columns for one or more input values, says P and Q, and one assigned column for the output results. The output which we get here is the result of the unary or binary operation performed on the given input values. Resulting truth value of a new or compound statement is for all the possible truth values of the given original proposition. A table with n propositions has 2 raised to the power of n rows of truth value. Conditional is any two statements that are combined by the word if and then. It is also called a conditional statement or an implication. It is denoted by P with an arrow pointing Q, which is read as P implies Q, or if P, then Q. We also have derived conditionals. These are conditional statements that can be derived from the conditional statement. We have the given conditional, the converse, the inverse, and the contrapositive. Biconditional, on the other hand, is any two statements that are combined by the word if and only if, denoted by P with an arrow pointing both P and Q, which is read as P if and only if Q, or P is a necessary and sufficient condition 4Q. Compound statement, regardless of the truth values of the propositions that occur, is tautology, contradiction, and contingency. Tautology is if it is always true. You can think of a tautology as a rule of logic. Contradiction if it is always false. False for every assignment of truth values to its simple components. And contingency, neither a tautology nor a contradiction.
Hello, I am Joanna Batay, and for this slide, I will be sharing with you the things I learned from Mathematical Logic Part 2, which includes the logical equivalence and the laws of logical propositions. So what is logical equivalence? In logical equivalence, two statements are logically equivalent if their truth tables are identical or two statements are provable from one another. This means that the first statement implies the second statement, and the second statement also implies the first one. So for example, the converse and the inverse of a conditional are logically equivalent. They are logically equivalent since the inverse is the contrapositive of the converse. The contrapositive of a conditional statement both swaps the hypothesis and the conclusion, and negates both the hypothesis and the conclusion as well. Next example is we have here, if a number is divisible by 14, then it is divisible by 2 and 7. Likewise, if a number is divisible by 2 and 7, then it is divisible by 14. So these two statements are logically equivalent. So there are 12 laws of logical proposition that will be used to prove a statement. The identity laws, domination laws, idempotent, negation, double negation, commutative, associative, distributive, De Morgan's laws, absorption laws, conditional equivalence, and the biconditional equivalence. So just a note by T and F, a tautology and a contradiction respectively. And we have the following properties for any propositional variables such as the P, Q, and R. So now let us all recall the following laws of logical proposition. So it may not be easy to memorize the names of all these properties. However, they should all make sense to you. So the important name is the De Morgan's laws. Now let us explain them in words and compare them to similar operations on the real numbers. So first is we have here the identity laws. Compare them to the equation x times 1 is equal to x. The value of x is unchanged after multiplying by 1. We call the number 1 the multiplicative identity. For logical operations, the identity for disjunction is f and the identity for conjunction is t. So now, next is the domination laws. Compare them to the equation x times 0 is equal to 0 for real numbers. The result is always 0, regardless of the value x. So the 0 for disjunction is t and the 0 for conjunction is f. In the idempotent laws, when an operation is applied to a pair of identical logical statements, the result is the same logical statement. Compare this to the equation x to the power of 2 is equal to x, where x is a real number. It is true only when x is equal to 0 or x is equal to 1. But the logical equivalences p or p is equivalent to p, and p is equivalent to p are true for all p. In logic, negation is an operation that essentially takes a proposition P to another proposition not P, which is interpreted intuitively as being true when P is false and false when P is true. So, in propositional logic, double negation is the theorem that states that if a statement is true, then it is not the case that the statement is not true. So, next is the commutative laws. So, in commutative laws, they say that the order of operation does not matter. So it does not matter which of the two logical statements comes first. The result from conjunction and disjunction always produces the same truth value. Compare this to addition of real numbers. X plus y is equal to y plus x. Subtraction is not commutative because it is not always true that x minus y is equal to y minus x. So this explains why we have to make sure that an operation is commutative. So next is the associative law. It also said that the order of operation does not matter. However, there is a key difference between them and the commutative laws. The important consequence of the associative law is, since it does not matter on which pair of statements we should carry out the operation first, we can eliminate the parentheses and write, for example, P or Q or R without worrying about any confusion. In the distributive laws, when we mix two different operations on three logical statements, one of them has to work on a pair of statements first, forming an inner operation. So this is followed by the outer operation to complete the compound statement. Distributive laws say that we can distribute the outer operation over the inner one. So next is the De Morgan's law. In the De Morgan's laws, when we negate a disjunction as respectively a conjunction, we have to negate the two logical statements and change the operation from disjunction to conjunction. Next is the absorption laws. So it is a valid argument form and rule of inference of propositional logic. The rule states that if P implies Q, then P implies P and Q. The rule makes it possible to introduce conjunctions to proofs. It is called the law of absorption because the term Q is absorbed by the term P in the consequent. And lastly, the conditional and biconditional equivalence, which was already mentioned from the previous reporter. So that is all the laws of logical proposition. So that is all for me, and thank you for listening.
Good morning, everyone. I am Liam Michelle D. Pinatil, and in this part of the video, I'm going to tackle about the methods of proof, what I've learned about it, and my reflection on it. A proof is a logical argument that tries to show that the statement is true. In math and computer science, a proof must be well thought out and tested before being accepted. But even then, a proof can be discovered to have been wrong. There are many ways to go about proving something. 3 methods, direct proof, proof by contradiction, and proof by contrapositive, had enticed me and what have made the most impact over the course of the subject. I am saying that these 3 methods have enticed me in an exhausting way, as I was literally having a hard time figuring and understanding them. We have learned these methods in the previous school years, but the feeling of not being able to understand anything has plagued me once again. I was brought back to the memories of hopelessness I once had, though this time, I can say that it was a bit easier and more understandable since we were taught simpler techniques, and I had the time to fully grasp the concept of these methods. One terminology has helped me in understanding and learning more about using these methods as proofs. A theorem is a mathematical statement which is proven to be true. A statement that has been proven true to further help in proving another statement is called a lemma. Direct proofing is that many theorems state that a specific type or occurrence of an object exists. One method for proving the existence of such an object is to prove that P implies Q. In other words, we would demonstrate how we would build that object to show that it can exist. A proof by construction or direct proofing is just that. We want to prove something by showing how it can come to be. There are only 2 steps to a direct proof. First is assume that P is true, and second is use P to show that Q must be true. In proof by contradiction, it can be used to prove any statement in several fields of mathematics. The structure is simple. assume that the statement to be proven is false, and work to show its falsity until the result of the assumption is a contradiction. Here are the steps that I follow when I must prove a mathematical statement using contradiction. First is assume your statement to be false. Second, proceed as you would with a direct proof. Third, come across a contradiction. And lastly, state that because of the contradiction, it can't be the case that the statement is false, so it must be true. And in the last method, a proof by contraposition is a type of proof used in mathematics and is a rule of inference. In logic, the contrapositive or contraposition of a statement can be formed by reversing the direction of inference and negating both terms. So in conclusion, we looked at a few different types of proofs and how they really work. We can use these methods to make logical arguments about the validity of some statement in our everyday lives, or in the code that we write, or in countless of other situations.
And now, the following is another part of the methods of proof. As soon as we hear the word proof, there are actually a lot of things that we can infer from it, considering the fact that the word itself is widely used in a variety of fields. However, in mathematics, we can most likely think of the different methods of proof used, in which proof is regarded as a series of statements that forms the argument. And from the different methods of proof, one thing that I could say is notable for me is the principle of mathematical induction. This principle of mathematical induction is one such method that could be employed to prove a broad range of mathematical propositions. Each such statement is considered to be Pn, associated with a positive integer n, and its validity for the case n equals to 1 is tested. The truth of p, k plus 1 is then verified by assuming the truth of pk for some positive integer k. Therefore, as what I have learned from this, mathematical induction is a way of proving a mathematical statement by saying that if the first case is true, then all the other cases are true. This is why, despite it being an induction, it is a method of deduction. Furthermore, this has two cases, wherein the first is to prove that our first case is true, while the second is to prove that if any other case is true, then the following case is also true. Thus, if any one case is true, then the next is true also. And if this is the case, then it means that all the cases in any one particular problem are true. Finally, this principle doesn't just stop there, as this could be applied particularly in solving puzzles and in the commonly known domino effect.
So how does mathematics work in music and dance? So we have the term similarities. There are lots of similarities in every dance, and they all use angles, geometry, shapes, line, segment, diamond, parallel, and right angle. For the application, we have the example of ballet dancing. They use physics to calculate the when to lift the partner and with correct power. And in hip-hop, we consider the beat of the right timing. We also have an example here in Philippines, which is the folk dances. They have the correct beat, which uses numbers such as vinyasa or specifically the waltz movement. Now let's tackle the three elements of dance. First is space. So where does the dancer move? Of course, through space. We're not talking about the final frontier, but we're talking about where the action of dance takes place. Dance moves through space in an endless variety of ways. Second is time. How does the body move in relation to time? So choreographers have to make decisions about timing, and their movements are either quick or slow. And there are also certain steps repeated in different speeds during the work. If so, we can think of time in the following ways. So first is clock time. We use clock time to think about the length of a dance or parts of the dance measured in seconds, minutes, or hours. Second is timing relationships. When dancers move in relation to each other, like before, after, together, or sooner than that, or faster than that, in the right timing. The third one is energy. So how the dancer moves through space and time with energy. So now that we have bodies moving through space and time, is that enough? Not quite. So we need the third and last element of dance, which is the energy. Energy helps us to identify how the dancers move, what effort are they using, and perhaps their movement are sharp and strong, or maybe they are light and free. Energy also represents the quality of movement, its power, and its richness. For choreographers and dancers, there are many responsibilities. Dance patterns may be described according to combinations of quick and slow step and often by rhythm or meter of the music. For example, as was said earlier in Cariñosa, we specifically have the waltz step. They use the 3-count step patterns dance to waltz music. In the swing step, we use the 4-count patterns dance to swing music. Mathematics and network. So network is a set of objects that are connected together, and in math we refer to it as graphs. For the meaning of edges, they are the connections between the vertices and the graph. In network, it is an ordered pair of the set of vertices or node or point and is denoted by the VG, link, or lines. Vertex set VG has its element called vertices, which is the vertex for singular, and nodes or points, with the cardinality of the absolute value of V and G and is ordered of the graph G. We also have the edge set of EG, and it has its element called edges or link or lines, and with the cardinality of EG as the size of the graph G. These graph mentions are the symbol undirected graphs. We also have the vertices V and U, which is adjacent to each other. The edge E is incident with vertex U and also incident with vertex V. The isolated vertex is the degree of vertex V, and the disconnected graph are graph G, which has an isolated vertex. For example, one could describe the internet as a network, wherein the nodes are computers and other devices, and the edges are the physical or wireless connection between the devices. Now let's apply it for some examples. So graph is a pair of VE of two sets here, wherein the V is a set of elements called vertices and E is the set of pairs of vertices called edges. So for example, G is equal to VE, wherein the set of elements of V is 1, 2, 3, and 4, and the set of pairs of vertices of E, which is the edge, is 1, 2, 1, 3, 2, 3, and 3, 4. So we notate this one as G is equal to VE for a graph with vertex set V and edge set of E, in which VG is the vertex set of G and EG is the edge set of G.